before there was anything, there was something stranger than nothing. The quantum vacuum, a seething ocean of virtual particles, flickering in and out of existence on timescales so brief, they make a nanosecond seem like an eternity. This is where our story begins, not with absolute nothingness, but with a state of reality so peculiar that physics itself begins to blur into philosophy. The quantum vacuum is never truly empty. Even in the darkest void of space, far from any star or galaxy, particles and antiparticles spontaneously emerge from the fabric of space-time itself, borrowing energy from the uncertainty principle. They exist for infinitesimal moments before annihilating each other, paying back their borrowed energy debt to the universe. This isn't speculation or metaphor. It's a measurable phenomenon that shows up in laboratory experiments, creating tiny forces between metal plates in a vacuum, an effect called the Casimir effect. Think about what this means. The universe's baseline state isn't stillness or emptiness. It's a roiling quantum foam where the laws of physics themselves become uncertain at the smallest scales. At distances smaller than 10 to the negative 35 meters, what physicists call the Planck length, our conventional understanding of space and time breaks down completely. Space might not be smooth and continuous, but grainy, pixelated, made of discrete quantum units that can't be subdivided further. This quantum foam doesn't just sit there passively. It has energy. Even empty space carries an energy density, what Einstein called the cosmological constant. This vacuum energy creates a repulsive pressure, a negative gravity that pushes space apart rather than pulling things together. Today, we observe this effect as dark energy, the mysterious force accelerating the universe's expansion. But in the earliest moments of the universe, this vacuum energy may have played an even more dramatic role. Imagine the universe 13.8 billion years ago, though time itself hadn't quite started yet. There was no before in any meaningful sense, because time emerges along with space as part of space-time. The concept of causation starts to break down. What caused the universe to begin? The question might be meaningless, like asking what's north of the North Pole. Time is part of the universe, not something the universe exists within. The first moment we can describe with any confidence is the Planck epoch, the first 10 to the negative 43 seconds after the beginning. This is unimaginably brief. If you tried to count that many instants, and you could count 1 trillion per second, it would take you longer than the current age of the universe to count them all. During this Planck epoch, the universe was smaller than an atom, compressed to densities we can barely conceive. All 4 fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single force. The temperature exceeded 10 to the 32 degrees Kelvin. At these temperatures, our current physics breaks down. General relativity, our theory of gravity and space-time, conflicts with quantum mechanics, our theory of particles and forces. We need a theory of quantum gravity to describe what happened, and we don't have one yet. String theory, loop quantum gravity, and other approaches offer possibilities, but none are confirmed. What we think happened during this epoch is that quantum fluctuations in the unified force field created ripples in space-time itself. These weren't fluctuations in something existing within space. They were fluctuations of space. The distinction is crucial. When we say the universe emerged from nothing, we don't mean from absolute philosophical nothingness. We mean from a quantum state with no classical particles, no matter, no radiation, but still governed by physical laws and containing quantum fields. One particular quantum fluctuation, through a process still not fully understood, triggered what we call cosmic inflation. This is one of the most important and peculiar events in cosmic history. Yet it happened so early and so briefly that its entire duration fits comfortably within the first second of existence. Inflation was proposed by physicist Alan Guth in 1980 to solve several problems with the standard Big Bang model. The first problem is called the horizon problem. When we look at the cosmic microwave background, the afterglow of the early universe visible in all directions, we see that it has almost exactly the same temperature everywhere. The temperature varies by only about 1 part in 100,000 across the entire sky. This seems natural until you realize that regions of space on opposite sides of the sky were never close enough together to exchange heat or information. They're outside each other's light cones. They should have no reason to be at the same temperature, yet they are. The second problem is the flatness problem. The geometry of space can be curved, either positively like the surface of a sphere, or negatively like a saddle shape, or it can be flat like an infinite sheet of paper. Our universe appears to be extraordinarily flat. For it to be this flat today, it would have had to be even flatter in the early universe, fine-tuned to an absurd degree. Why would the universe start with such a specific geometry? Inflation solves both problems elegantly. In a period lasting perhaps 10 to the negative 32 seconds, space expanded exponentially. Not just rapidly, but exponentially, doubling in size every tiny fraction of a second. In less time than it takes light to cross an atomic nucleus, the universe expanded by a factor of at least 10 to the 26th, possibly much more. Some calculations suggest the expansion factor could have been 10 to the 100 or even larger numbers that make those pale in comparison. This expansion was driven by a scalar field called the inflaton field, which temporarily had enormous energy density. This wasn't like ordinary matter or radiation expanding into space. Space itself was expanding, carrying everything with it. During inflation, regions of space separated faster than light could travel between them. This doesn't violate relativity, because nothing was moving through space faster than light. Space itself was expanding. Here's what inflation accomplished. It took a tiny patch of space, small enough that all parts of it were in thermal contact, and thus at the same temperature, and expanded it to become larger than our currently observable universe. This explains why distant regions have the same temperature. They were once close enough to equilibrate before inflation separated them. Inflation also stretched space so flat that any initial curvature became undetectable, like blowing up a balloon until its surface appears flat locally. A small curved surface becomes a huge, nearly flat surface. But inflation did something even more remarkable. Those quantum fluctuations in the inflaton field, tiny random variations at the quantum scale, were stretched by inflation to cosmic sizes. These quantum ripples became the seeds of all structure in the universe. Regions slightly denser than average would attract more matter through gravity, eventually collapsing to form the first stars, galaxies, and galaxy clusters. The cosmic microwave background maps show these variations as tiny temperature differences. We're seeing quantum fluctuations from the first moments of existence written across the sky. When inflation ended, the inflaton field decayed. Its enormous energy had to go somewhere. This energy transformed into the hot, dense soup of particles and radiation that filled the early universe. This reheating process created matter and antimatter in equal amounts, at temperatures exceeding 10 to the 27 degrees Kelvin. The universe was still far too hot for atoms to exist. Even atomic nuclei couldn't hold together. All that existed were free quarks and leptons swimming in a sea of photons. As the universe continued to expand and cool, it went through a series of phase transitions, similar to how water transitions from steam, to liquid to ice, but far more exotic. The first major transition occurred when the universe was about 10 to the negative 11 seconds old. The temperature had dropped to around 10 to the 15 degrees Kelvin, cool enough for the strong nuclear force to separate from the electro-weak force. This is called the quark epoch. During this transition, something remarkable and still somewhat mysterious happened. Quarks began to bind together through the strong nuclear force, forming the first protons and neutrons. But there's a problem here, one of the deepest mysteries in physics. The laws of physics as we understand them should have created exactly equal amounts of matter and antimatter. Every quark should have had an antiquark partner. When matter and antimatter meet, they annihilate, converting their mass entirely to energy. If the universe had contained exactly equal amounts, everything should have annihilated, leaving only radiation. Yet here we are, made of matter, surrounded by a universe of matter. There's almost no antimatter anywhere in the observable universe. Something created an asymmetry, a slight excess of matter over antimatter. For every 10 billion antiquarks, there were 10 billion and 1 quarks. That tiny difference, 1 part in 10 billion, became everything we see today. The 10 billion pairs annihilated, and the 1 leftover quark in every 10 billion survived to become the matter in our universe. This process is called baryogenesis, the creation of matter. We know it must have happened, but we're not entirely sure how. The physicist Andrei Sakharov proposed 3 conditions necessary for baryogenesis to occur. First, there must be interactions that violate baryon number conservation, meaning processes that create or destroy protons and neutrons. Second, both charge conjugation and parity symmetry must be violated. This means the laws of physics must treat matter slightly differently than antimatter. Third, these processes must occur out of thermal equilibrium, meaning the universe must be cooling rapidly enough that reactions don't have time to reach equilibrium and erase any asymmetry. The standard model of particle physics includes some violation of these symmetries, observed in experiments with particles called kaons and b-mesons. But the amount of violation predicted by the standard model is too small to explain the observed matter-antimatter asymmetry. This suggests new physics beyond the standard model was involved in the early universe. Some theories propose new particles or interactions that existed at high energies, but decayed away as the universe cooled. Others invoke connections to neutrino physics, or even exotic phenomena in the first moments of inflation. By the time the universe was 1 microsecond old, it had cooled to about 10 to the 13th degrees Kelvin. Quarks and gluons had combined to form protons and neutrons, the building blocks of atomic nuclei. But it was still far too hot for these protons and neutrons to stick together. The photons flying around had enough energy to blast apart any nucleus that tried to form. During the next few minutes, as the universe cooled from billions to millions of degrees, a crucial process occurred called Big Bang nucleosynthesis. Protons and neutrons began to fuse together, creating the first atomic nuclei heavier than hydrogen. This process started when the universe was about 1 second old and essentially finished by the time it was 20 minutes old. The physics of nucleosynthesis is well understood because it involves the same nuclear reactions that power stars and hydrogen bombs, just occurring throughout space rather than in localized regions. When the temperature dropped below 1 billion degrees Kelvin, neutrons and protons could combine to form deuterium, heavy hydrogen, with 1 proton and 1 neutron. This is a crucial step because deuterium is relatively fragile. At higher temperatures, photons destroy deuterium as fast as it forms. Once deuterium could survive, nuclear reactions proceeded rapidly. Deuterium nuclei fused to form helium-3, 2 protons and 1 neutron, and helium-4, 2 protons and 2 neutrons. Some lithium-7, 3 protons and 4 neutrons, also formed in tiny amounts. But the rapid expansion and cooling of the universe shut down these reactions before heavier elements could form. There's a gap in nuclear stability. No stable nuclei exist with 5 or 8 nucleons, so the fusion chain can't proceed past lithium in the early universe. The outcome of Big Bang nucleosynthesis is remarkably predictable and matches observations beautifully. About 75% of the ordinary matter remained as hydrogen, single protons. About 25% became helium-4. Trace amounts of deuterium, helium-3, and lithium-7 also formed. This ratio depends on the density of ordinary matter and the expansion rate of the early universe. When we measure the abundances of these light elements in the oldest stars and gas clouds, they match the predictions precisely. This is one of the strongest pieces of evidence supporting the Big Bang model. But here's something profound to consider. Every atom of helium in your breath, in the sun, in the heart of distant stars, was forged in those first 20 minutes after the Big Bang. Stars make heavier elements through fusion, creating carbon, oxygen, iron, and all the other elements up to uranium. But the helium was mostly there from the beginning, a cosmic fossil from the universe's infancy. After nucleosynthesis ended, the universe entered a long period called the photon epoch. For the next 380,000 years, the universe was a hot, glowing plasma. Electrons couldn't attach to nuclei to form atoms because photons had enough energy to knock them loose. This plasma was opaque. Light couldn't travel far before being scattered by free electrons. Think of it like being inside a glowing fog. You're surrounded by light, but you can't see distant objects because the light keeps bouncing off fog droplets. In the early universe, photons kept bouncing off electrons. The mean free path of a photon, the average distance it could travel before being scattered, was extremely short. The universe was filled with light, but was not transparent. As the universe expanded, it cooled. The photons redshifted to lower energies, losing energy not because they were slowing down, but because space itself was stretching, increasing their wavelengths. When the temperature dropped to about 3,000 degrees Kelvin, roughly half the surface temperature of the Sun, something remarkable happened. Electrons had just little enough energy to be captured by nuclei, forming the first neutral atoms. This process is called recombination, though it's a misleading term since the electrons and nuclei had never been combined before. When electrons joined with nuclei to form atoms, the universe suddenly became transparent. Photons no longer had free electrons to scatter off. Light could travel unimpeded across cosmic distances. The universe went from glowing plasma to clear darkness. The light that was scattered one last time during recombination has been traveling through space ever since. Today, 13.8 billion years later, we detect it as the cosmic microwave background radiation. The expansion of the universe has stretched its wavelength by a factor of about 1,100, cooling it from 3,000 degrees Kelvin to just 2.7 degrees Kelvin, barely above absolute zero. This cosmic microwave background is one of the most important discoveries in the history of science. It was predicted by George Gamow and his colleagues in the 1940s as a consequence of the Big Bang model. When Arno Penzias and Robert Wilson accidentally discovered it in 1964 while testing a radio antenna, they found a mysterious hiss coming from all directions. After ruling out interference from everything, including pigeon droppings in their antenna, they realized they were detecting the afterglow of the Big Bang itself. cosmic microwave background has been measured with increasing precision by satellites including the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite. These measurements reveal that the early universe was remarkably uniform. The temperature varies by only about 18/10 of a degree across the sky. But those tiny variations are crucial. They map the density variations created by quantum fluctuations during inflation, the seeds that would grow into galaxies. After recombination, the universe entered what's called the Dark Ages. With no stars yet formed, the universe was truly dark. Hydrogen and helium gas drifted through space, gradually collecting into denser regions under gravity's pull. These weren't gentle processes. Gas clouds collided and merged. Denser regions attracted more gas. Where density variations were strongest, gas collapsed faster. The first stars began to form about 100 million years after the Big Bang, though the exact timing is still uncertain. These weren't like modern stars. They formed from pure hydrogen and helium, with no heavier elements to help cool the gas and allow smaller stars to form. As a result, the first stars were monsters, perhaps hundreds of times the sun's mass, burning fiercely hot and bright, but living only a few million years before exploding. These first stars are called population 3 stars, though none have ever been observed directly. They would have been so rare and short-lived that finding one would require extraordinary luck, like winning a lottery where the odds are measured in trillions. But we know they must have existed because they created the first heavy elements through nuclear fusion in their cores and scattered them across space when they exploded as supernovae. These explosions seeded space with carbon, oxygen, silicon, iron, and other elements. Subsequent generations of stars formed from gas, enriched with these elements. Our Sun is a third-generation star at minimum, formed from gas that has been through multiple cycles of stellar birth and death. Every atom in your body heavier than hydrogen was forged in the nuclear furnace of a star or in the violent explosion of a supernova. The first galaxies began to form a few 100 million years after the Big Bang. These were small, irregular galaxies, nothing like the majestic spirals we see today. They were chaotic assemblies of stars, gas, and dark matter, constantly merging and colliding. The James Webb Space Telescope has now observed galaxies forming less than 500 million years after the Big Bang, seeing them as they were in the universe's infancy. These observations reveal that galaxy formation was a messy, violent process. Young galaxies blazed with intense star formation, creating thousands or millions of new stars per year, compared to the few per year in the Milky Way today. They were compact and dense, with stars packed much closer together than in modern galaxies. Many hosted supermassive black holes already, millions or billions of times the sun's mass, though how black holes grew so large so quickly remains mysterious. Dark matter played a crucial role in all of this. This invisible substance, detected only through its gravitational effects, makes up about 85% of all matter in the universe. During the early universe, dark matter began collecting into vast cosmic structures under its own gravity. These dark matter halos created gravitational wells that attracted ordinary matter, helping gas clouds collapse to form stars and galaxies. We still don't know what dark matter is made of. It's not ordinary matter made of protons and neutrons. It doesn't interact with light, making it invisible to telescopes. The leading candidates are exotic particles that barely interact with ordinary matter. Perhaps a new type of particle, predicted by supersymmetry or other theories, beyond the standard model. Experiments deep underground and at particle accelerators continue searching for direct evidence of dark matter particles, so far without success. As galaxies grew through mergers and accretion, they began organizing into larger structures. Galaxy groups formed first, then galaxy clusters containing hundreds or thousands of galaxies. These clusters themselves aligned along vast filaments, creating a cosmic web that spans the universe. Between the filaments lie enormous voids, regions with very few galaxies, some hundreds of millions of light-years across. This large-scale structure, formed from those tiny quantum fluctuations during inflation, amplified by billions of years of gravitational growth. Computer simulations can reproduce this structure remarkably well, starting from the initial conditions set by the cosmic microwave background and evolving forward using only gravity. The simulations match observations, providing powerful confirmation that we understand how the universe evolved from smooth early conditions to the complex web of galaxies we see today. But there's a puzzle here, one that emerged only in the late 1990s. Astronomers studying distant supernovae, using them as standard candles to measure cosmic distances, discovered something unexpected. The expansion of the universe is accelerating. Not just expanding, but expanding faster and faster as time goes on. This discovery was shocking because gravity should slow the expansion. Matter and energy create gravity, which attracts things together. The universe should be either expanding and slowing down, or collapsing. But observations showed the opposite. Something is pushing space apart with ever-increasing strength. This mysterious something is called dark energy, and it makes up about 68% of the total energy density of the universe. We don't know what it is. The simplest explanation is that it's the cosmological constant, the vacuum energy of empty space itself. Remember that quantum vacuum we discussed at the beginning, with its virtual particles and baseline energy. That energy creates a repulsive pressure. Einstein originally introduced the cosmological constant to make his equations yield a static universe, then called it his greatest blunder when Edwin Hubble discovered the universe was expanding. But it turns out empty space really does have energy. The problem is that when we calculate how much vacuum energy quantum field theory predicts, we get an answer about 10 to the 120 times larger than what we observe. This is called the cosmological constant problem, and it's one of the deepest puzzles in physics. The expansion history revealed by studying distant supernovae, combined with observations of the cosmic microwave background and surveys of galaxy clustering, paints a detailed picture of cosmic evolution. The universe started in a hot, dense state, cooled and expanded, slowed by matter's gravity for the first several billion years, then began accelerating as dark energy's repulsive effect became dominant. About 5 billion years ago, when the universe was roughly half its current age, dark energy began to dominate. The universe's expansion started accelerating. Galaxy clusters stopped growing, as new galaxies could no longer fall into them against the accelerating expansion. The future became one of increasing isolation, with galaxy clusters moving apart faster and faster. This brings us to a profound realization. The universe we can observe, everything within about 46 billion light-years, is just a tiny fraction of what exists. During inflation, our observable universe was a minuscule patch, smaller than an atom, that got stretched to cosmic sizes. But inflation didn't stop everywhere at once. While inflation ended in our patch, creating the Big Bang that led to us, it continued in other regions, creating other universes. This is the idea of eternal inflation. Quantum fluctuations in the inflaton field randomly cause it to decay in some regions, while remaining energized in others. Each region where it decays becomes a universe, a bubble expanding into its own separate space. These bubbles are causally disconnected from each other. We can never observe or interact with them because they're beyond our cosmic horizon. In each bubble universe, the laws of physics might be different. The constants of nature, like the strength of gravity or the mass of the electron, might vary. The number of dimensions, the types of particles, the forces, all could be different. Most of these universes would be sterile, unable to form stars or support life. We exist in a universe where the constants happen to allow complexity. This leads to the anthropic principle. We observe the universe having properties compatible with our existence, not because those properties are necessary or special, but because we couldn't exist in universes with different properties. It's a selection effect. In a vast multiverse with countless bubble universes having different physical laws, observers will only arise in universes capable of supporting observers. Some find this unsatisfying, arguing it gives up on explaining why our universe has the properties it does. Others argue it may be the only answer possible if the multiverse is real. We may never know which interpretation is correct, because the other bubble universes are forever beyond our reach, hidden behind horizons we can never cross. Looking forward in time, the future of our universe depends on dark energy. If dark energy remains constant, as current evidence suggests, the universe will continue expanding forever. The expansion will accelerate, carrying distant galaxies away from us faster and faster. In about 100 billion years, every galaxy outside our local cluster will have crossed the cosmic event horizon, receding faster than light and becoming forever unreachable. Future astronomers in that distant epoch will see a very different sky. They'll observe only the merged galaxy formed from the Milky Way, Andromeda, and a few dozen smaller galaxies in our local group. Beyond that, empty darkness. They'll have no way to discover the Big Bang, cosmic expansion, or other galaxies. The universe will have erased its own history. Eventually, in perhaps a Google years, 10 to the 100 years, the last stars will burn out. Brown dwarfs and white dwarfs will cool to black dwarfs. Even black holes will evaporate through Hawking radiation, though this takes unimaginably long for large black holes. The universe will approach a state of maximum entropy, the heat death, where nothing changes because all energy gradients have disappeared. But perhaps dark energy will change. If it's not a constant but a field that evolves, it might weaken, allowing gravity to reverse the expansion and cause a big crunch. Or it might strengthen, tearing apart galaxies, stars, planets, atoms, and eventually even space-time itself in a big rip. We don't know. Dark energy remains one of the greatest mysteries in science. Other cosmological models propose different possibilities. Conformal cyclic cosmology, proposed by Roger Penrose, suggests the universe goes through infinite cycles of expansion, heat death, and rebirth. In this model, the infinite far future of one universe becomes the Big Bang of the next. The ekpyrotic universe model proposes that the Big Bang was caused by colliding higher dimensional membranes. Loop quantum cosmology suggests the Big Bang was actually a big bounce, a contraction of a previous universe that reached maximum density and rebounded into expansion. These are speculative ideas, attempts to understand what came before the Big Bang, or what the ultimate fate of the universe will be. They're difficult to test because they make predictions about conditions far beyond what we can currently observe. But they remind us that our understanding remains incomplete. The story of how nothing, or rather, the strange quantum something that is the vacuum state, became everything, is one of the most profound discoveries humans have made. We've traced the universe from quantum fluctuations at the Planck scale through inflation, through the hot, dense early universe, through nucleosynthesis and recombination, through the formation of the first stars and galaxies. to the vast cosmos we inhabit today. Every step has been confirmed by observations. The abundances of light elements match Big Bang nucleosynthesis predictions. The cosmic microwave background exists exactly as predicted and shows the temperature variations from quantum fluctuations. The large-scale structure of galaxies matches computer simulations based on those fluctuations. The accelerating expansion has been measured through multiple independent methods. Yet mysteries remain. What caused inflation? What is dark matter? What is dark energy? What happened at the very beginning, during the Planck epoch, when quantum gravity effects dominated? Are there other universes? Will our universe end, and if so, how? These questions drive current research in cosmology and particle physics. Experiments at the Large Hadron Collider search for new particles that might be dark matter. Telescopes study the cosmic microwave background in ever finer detail, looking for signatures of inflation and hints about what came before. Gravitational wave detectors listen for ripples in spacetime from the early universe. Surveys map billions of galaxies to understand dark energy's effects. The instruments keep getting better. The James Webb Space Telescope can see farther back in time than ever before, observing the first galaxies forming. The Vera Rubin Observatory will survey the entire visible sky every few nights, tracking changes and discovering millions of cosmic events. The Square Kilometre Array will be the most sensitive radio telescope ever built, potentially detecting signals from the cosmic dark ages before the first stars formed. Each observation refines our understanding, answering some questions while raising new ones. Science proceeds this way, building on what came before, testing predictions, revising theories when observations demand it. The Big Bang theory itself has evolved substantially since first proposed. The addition of inflation, the discovery of dark matter and dark energy, the understanding of structure formation, all these represent major advances. What seemed impossible to know just decades ago is now measured with precision. We know the age of the universe to within 1%. We know its composition, the ratios of ordinary matter, dark matter, and dark energy. We know how fast it's expanding. We know what it looked like just 380,000 years after the beginning, and have strong evidence about what happened in the first microseconds. This represents one of humanity's greatest intellectual achievements, rivaling anything in art, literature, or philosophy. We've used mathematics, physics, and painstaking observation to reconstruct the history of everything. We've seen our cosmic origins written in the sky, in the abundances of elements, in the leftover heat from creation itself. Think about what this means for our place in the universe. Every atom in your body was once part of the hot, dense plasma filling space just after the Big Bang. The hydrogen in your water molecules formed in the first second. The carbon in your cells was forged in stars that died billions of years ago. The calcium in your bones might have come from a supernova explosion that briefly outshone an entire galaxy. You are made of stardust, quite literally, but you're also made of the primordial material from the beginning of time. The quantum fluctuations that seeded galaxies also seeded everything within those galaxies. The matter that became you was spread across billions of light years in the early universe, slowly collecting together through gravity over cosmic timescales. On one level, this makes us cosmically insignificant. We're tiny arrangements of matter on a small planet, orbiting an ordinary star in a galaxy of billions, in a universe of trillions of galaxies. Our entire existence spans a cosmic eye blink compared to the age of the universe. Everything we've ever known or cared about occurs in one tiny corner of space-time. But on another level, it makes us cosmically significant. We're the universe looking at itself, matter arranged in patterns complex enough to contemplate existence. The universe spent 13.8 billion years creating the conditions for complexity, for chemistry, for life, for consciousness. We're part of that story, products of cosmic evolution, from quantum fluctuations, to atoms, to stars, to planets, to life, to minds capable of understanding it all. The laws of physics that governed the first moments after the Big Bang are the same laws operating now. The forces that shaped the early universe shape our world today. By studying the cosmos, we're learning about the deep principles underlying reality itself. Every discovery about the early universe teaches us something about the nature of matter, energy, space, and time. And the story continues. The universe is still evolving, still changing. Stars are still forming. Galaxies are still merging. The expansion is still accelerating. We exist during a particular chapter of cosmic history, when stars shine brightly, when galaxies cluster together, when the cosmic past is still visible in the sky. This won't last forever. We live in a special time, a brief window when intelligent life can arise and understand its cosmic context. Appreciating this perspective doesn't require giving up other ways of finding meaning. Science describes how things work, the mechanisms and processes. It doesn't address questions of purpose or value, which operate on different levels. Understanding that we emerged from the Big Bang through billions of years of cosmic and biological evolution can coexist with other frameworks for making sense of existence. What the Big Bang story gives us is context, a framework for understanding our origins and our place in the grand scheme. It connects us to the cosmos, showing that we're not separate from the universe, but integral parts of it. The carbon atoms in our DNA once floated free in space, scattered by dying stars. The calcium in our bones was synthesized in stellar furnaces. The iron in our blood was created in supernova explosions. This cosmic perspective can be humbling and inspiring simultaneously. Humbling because it reveals how small we are in space and time. Inspiring because it shows we're part of something vast and ancient, that the same processes operating across billions of light years and billions of years also operate in our bodies and brains. The journey from quantum fluctuations to consciousness represents perhaps the most remarkable transformation in cosmic history. Simple quantum fields evolved into complex structures, atoms into molecules, molecules into life, life into intelligence. Each step built on what came before, adding new levels of organization and complexity. Understanding this helps us appreciate both continuity and novelty. We're continuous with the rest of the cosmos, made of the same matter and governed by the same laws. But we're also genuinely new, a different kind of thing than stars or atoms or quantum fields. Consciousness, whatever its ultimate nature, represents an emergent phenomenon, something that arises from complexity, but has properties not present in the simpler components. The Big Bang itself, that moment of cosmic beginning, remains wrapped in mystery. We can trace the universe back to the Planck epoch, but not beyond. What happened at the very beginning, whether time itself had a beginning or extends infinitely into the past, whether the universe came from nothing or from something. These questions probe the limits of current knowledge. Some mysteries may never be solved. We might lack the mathematical tools or conceptual frameworks to understand the ultimate beginning. The universe might be fundamentally incomprehensible in certain respects, with questions that have no answers, or answers that transcend human understanding. But this doesn't diminish what we have learned. The story from the Planck epoch onward is well established, supported by converging lines of evidence from multiple fields. We may not understand the ultimate beginning, but we understand cosmic evolution from 1 microsecond after the beginning until today. That's remarkable progress for creatures who evolved to find food and avoid predators, not to understand cosmology. Looking ahead, future discoveries will undoubtedly revise our understanding. New observations might overturn current theories or reveal new phenomena. Dark matter could turn out to be something completely unexpected. Dark energy might be explained by some new field or force. The multiverse might be confirmed or refuted. Quantum gravity might lead to radical new insights about space and time. Science is always provisional, always open to revision based on new evidence. But this doesn't mean current knowledge is worthless, or that all theories are equally valid. Some things are established beyond reasonable doubt. The universe is expanding. It was once much hotter and denser. The light elements were formed in the first minutes. The cosmic microwave background is real. These facts won't change even as our theoretical understanding deepens. The cosmic story from Big Bang to today provides a narrative framework for everything else. Geology becomes understandable as plate tectonics on a planet that formed from the disk around a young star. Biology becomes understandable as evolution operating on planets with liquid water and complex chemistry. Human history becomes understandable as recent developments of creatures who evolved on one particular planet. Everything connects. The quantum fluctuations during inflation led to density variations that led to the first galaxies, that led to generations of stars, that created heavy elements, that became planets, that developed life, that evolved intelligence, that built telescopes, that discovered the quantum fluctuations. The universe is a nested hierarchy of cause and effect, each level building on previous levels while adding new possibilities. Nothing was there, but then something was. Not an explosion, but an expansion. Not matter moving into space, but space itself carrying matter along. From quantum uncertainty to cosmic certainty, from formless energy to complex matter, from darkness to light to darkness again. The universe has journeyed through 13.8 billion years of change. And here we are, able to contemplate it all, to trace our lineage back to the beginning, to understand our cosmic context. We emerged from the Big Bang just as surely as stars and galaxies did. We're part of the story, late arrivals perhaps, but genuine participants in cosmic evolution. The atoms that think these thoughts, that form these words, that grasp these concepts, were forged in the Big Bang's aftermath and refined in stellar cores. We are the universe, examining itself,